Hello everyone, my name is Patricia Adame. I am the Senior Application Engineer for Saint-Gobain Tape Solutions. Today, I would like to show you the results of a study we've done to prove how high-performance foams can enhance the mechanical performance of non-woven thermal barriers intended for battery packs. Within this presentation, we will review some thermal barrier technologies. I will explain the task protocol that we followed to evaluate mechanical performance on such materials. We will also review what's the typical behavior of these thermal barriers under compression and how Saint-Gobain Norseal foams can enhance that mechanical performance. So let's get started. Ideally, battery pack engineers are looking for a material solution that can provide a dual function, such mechanical cushioning and thermal protection. This illustration on the left shows the cell-to-cell pad in between the cells. On the right, we see an explanation of two of the main functions for an intercell material. One is the mechanical performance to provide cushioning to the cells during the charge and discharge cycles, but also an optimal and consistent pressure to optimize the cell's capacity over time. Another quite important function is temperature resistance, where the material must prevent or mitigate the thermal runaway event, and ideally stop its propagation to the adjacent cells. There are a few material solutions in the market that are promoted as thermal barrier materials, which have good thermal performance, but no mechanical capabilities, such ceramic papers and mica sheets. For today's discussion, I will focus on non-woven solutions such as aerogel blankets and fiber mats. These two technologies also have good thermal resistance, and we will review their mechanical performance based on our testing protocol. Saint-Gobain R&D and technical teams have developed a custom testing protocol to screen the mechanical performance on such thermal barrier materials. In this stress versus strain graph, you can see a curve for the assembly pressure, which is usually tested at a higher speed than the following cycles, which intend to mimic the cell's breathing in the application. And we know this happens at a much slower rate than the assembly speed. There is also a minimum stress needed for the optimal cell's capacity retention and a not to exceed stress in order not to damage the cell. With this testing protocol, we tested up to 10 cycles in order to obtain a hysteresis curve, because we know that the consistent pressure over time is critical for the battery overall lifespan. This slide compares the mechanical behavior of aerogel and fiber mats thermal barriers. Depending on the technology, you can see that non-woven number 1 and number 4 seem to be closer to meet that minimum required pressure. However, with the cycles and the up to 10 cycle, that performance starts to drop and be below that minimum stress requirement. Another phenomenon is that the materials are not showing a rebound capability. So after the first compression, there is a gap in both the stress and the strain performance for all the following cycles. And that happened in all the 4 different materials that we were able to test. Another important disadvantage of these non-woven thermal barrier solutions is that they cannot provide a consistent pressure to the cells. As we have already discussed, this consistent pressure is critical for an optimal battery performance and to prolong its lifespan. Let's say we consider minimum value of 80 kPa pressure. This type of materials might perform during the initial compression, but as the fatigue happens and the cells breathe over time, you can see that in both graphs that mechanical performance keeps dropping. Also with the hysteresis, depending again on the materials technology, some of them might stabilize quite well, and some of them just keep dropping during the cycling testing. Saint-Gobain R&D team has great analysis capabilities and extensive knowledge on material technologies. Once they saw this compression behavior, they wanted to better understand what was happening to those non-woven materials. After the compression testing was completed, the team measured the thickness on those tested samples to compare the final versus the original thickness. You can see on this graph that all the 4 materials had a thickness change or a thickness loss after the test, being the non-woven number 2 and number 4 the most damaged ones. What happened to these materials at a deeper level is that the fibers broke during the compression cycles, and there was a reversible fiber friction that basically translates into this thickness loss under cyclic compression. Now, let's talk how Saint-Gobain High Performance Foams can help to enhance this mechanical performance for these non-woven thermal barriers. Saint-Gobain Tape Solutions has a wide portfolio of viscoelastic foam technologies such as polyurethane and silicone foams, and we know how well these materials behave under compression. Following the same testing protocol as the non-woven materials that we just reviewed, you can see that Norseal PF47-50 fatigue cycling remains in a small range, and the minimum stress under compression is always above that required minimum allowance. Also, there is initial hysteresis, stress loss. It stabilizes quite quick just after the second compression, so the material can provide a consistent pressure, which we already know how critical it is for the battery's overall lifespan. Knowing that there is not yet a material that by itself can provide a dual performance of mechanical capabilities and thermal runaway mitigation, we wanted to take the approach of combining the best of 2 worlds. So we tested a layer solution consisting of 1 layer of the non-woven material, and then we added a layer of Norseal PF47-50. On this slide, you can see how the mechanical performance was improved versus just testing the non-woven materials. The curves were achieving now that minimum stress, and they shifted to the right, closing that hysteresis gap between the first compression and the following ones. You can also see how that minimum stress, so to keep that consistent pressure, was improved. The same phenomenon happened with all the 4 non-woven materials that we were able to test. Here, not only the constant stress was addressed, but also the hysteresis stress stabilized much faster when testing the layer solutions versus just the non-woven material. Depending on the non-woven materials technology, so either in aerogel or a fiber mat, which are the ones that we're focusing on this study, the improvement might be more noticeable, like on this one. You can see how much improvement there was with both the minimum constant stress, but also the hysteresis curve. With the remaining sample, although the compression behavior improvement is not so clear in this stress versus strain graph, you can see in this upper right graph how the stress resilience under compression was improved. With this specific combination, the stress does not seem to stabilize after a few cycles. It keeps kind of dropping maybe up to cycle 6. So this shows how important it is to choose the proper combination that will provide the application performance needed on a case-by-case scenario. Saint-Gobain R&D team has developed a tool called Maxio, which requires some input from the application, such as the beginning of life and the end of life pressures that are expected in the modules. Also the assembly speed, just to mention a few. With this information and based on the stress versus strain data that we have gathered, the tool can suggest the foam solution at its optimal nominal thickness that would be the best fit for the application. But this tool can not only model our foams, we can even input the data on these non-woven materials, so the tool can give us an output on the optimized thickness for both the thermal barrier and the foam that will achieve the performance needed based on the customer needs. I would like to finish this presentation with a few takeaways. The first one is that typical non-woven thermal barriers show a progressively decline in mechanical performance under cyclic compression, which results in inconsistent pressure support to the batteries and will impact the battery's optimal performance and lifespan. On the other hand, Saint-Gobain Norseal foams maintain significantly more stable mechanical properties under the same circumstances, ensuring a consistent pressure on the cells. So, by combining Saint-Gobain Norseal foams with a non-woven thermal barrier, the mechanical performance can be enhanced, achieving both battery pack's optimal performance and safety goals. Thank you for your time today. I hope this content is helpful for when you are selecting materials for your battery pack designs. Please visit our website where you can learn more about our Norseal Foams portfolio, or feel free to reach out to me. I'll be happy to learn about your challenges and help overcome them. Have a great day.